Welcome you all, myself Rupanjali Goswami. In this video, we shall discuss on primitive roots. So for that, let us first define order of an integer mod m. So let m be a positive integer. If a and m are two integers such that their GCD is 1, or in other words, they are relatively prime, then the least positive integer r such that a to the power r congruent to 1 mod m is called the order of a mod m. Now the question is whether order of a always exists or not. For that, the answer is we have the Euler's theorem. By Euler's theorem, if a and m are relatively prime, then a to the power phi m is congruent to 1 mod m, provided a and m are relatively prime. So meaning is that when a and m are relatively prime, then I have phi m as the power on a, so that a to the power phi m is congruent to 1 mod m. Means this is satisfied. A to the power r congruent to 1 mod m is satisfied, in which r is phi m. So what I can say that when a and m are relatively prime, order of a mod m always exists. Now the question is, what will happen if a and m are not relatively prime? So let us see that case. So it is to be noted that if the GCD of a and m is greater than 1, then there exists no such r for which a to the power r is congruent to 1 mod m. Okay, so let us see what happens if a and m are not relatively prime. Suppose the GCD of a and m is d is greater than 1. Then by definition of GCD, d divides a and d divides m, and therefore what will happen if there exists an integer r satisfying a to the power r congruent to, if there exists an integer r such that, or satisfying a to the power r congruent to 1 mod m, then what will happen? Then actually by definition of congruence, I can say m divides a to the power r minus 1. And as d divides m, it is written there d divides m, so d will also divide a to the power r minus 1. So call this 1. Also we have seen d divides a. So d divides a to the power r also. Also d divides a implies d divides a to the power r. So call this 2. And we already have a result. Suppose d divides c and d divides e. Then this implies d divides c plus minus e. So we shall make use of that result here in 1 and 2. So from 1 and 2 I can write d divides a to the power r minus a to the power r minus 1. That means d divides 1. So what was d? But d was a number, it is greater than 1. So we have a contradiction. So this contradiction is obtained as we assume that there exists some integer r for which a to the power r congruent to 1 mod m. So in case when the GCD of a and m is more than 1, then there does not exist such r. Now let us take one example. Take m equal to 7. So m here is a prime. To find order of 1, 2, 3, 4, 5, 6 mod 7. Now we have as 1 congruent to 1 mod 7, so I can say that order of 1 mod 7 is 1. Then 2 cube congruent to 1 mod 7, because 2 cube is 8, 8 minus 1 is 7, 7 is divisible by 7. So order of 2 mod 7 is 3. Then I have 3 to the power 6 congruent to 1 mod 7. This gives order 3 mod 7 is 6. Then let us take 4 to the power 3. 4 cube is 64 minus 1 is 63 is divisible by 7. So order 4 mod 7 is 3. Then let us find 5 to the power 6 congruent to 1 mod 7, which gives order 5 mod 7 is 6. Then as we have 6 square 36 minus 1 is 35 divisible by 7. So I have order of 6 mod 7 is 2. So this way we can get order of 1, 2, 3, 4, 5, 6 mod 7. Now there is a result on order, so let us discuss it. If A and M are relatively prime, and if R is the order of A mod M, then number 1, 1a square up to a to the power r minus 1 are incongruent mod M. Number 2, if n is a positive integer, then there exists a unique integer s in the range (0 less than equal to s less than r), for which a to the power n congruent to a to the power s mod m. The third result on order is a power n congruent to 1 mod m if order r divides, if and only if divides n. And last one, a if b is congruent to a mod m, then order of b mod m equals the order of a mod m. Now let us prove these results, which are simple. So by the condition means, as it is told that r is the order of a, so r is the least positive integer for which a to the power r congruent to 1 mod m, where r is the least positive integer satisfying the congruence. Now let us see number 1. As we are to show that, let me show the result, which is in number 1. We are to show that 1 comma a square up to a to the power r minus 1. This r integers are incongruent mod m. So let us take on the contrary that any two of them are, say, congruent. Say a to the power I is congruent to a to the power j, where I and j are any two integers starting from, say, 0 to r minus 1. So let a to the power I congruent to a to the power j mod m, where I not equal to j, and let us take j to be greater than I and less than equal to r minus 1. Then we have a power I is congruent to, I can write a to the power j as a power I plus j minus I mod m. And here from this expression it is clear that j minus I is greater than 0. Okay, because I is strictly less than j. So j minus I is greater than 0. So this gives a to the power I congruent to a to the power I, a to the power j minus I mod m. And here, as a and m are relatively prime, this will give that a to the power I and m are also relatively prime. So by restricted cancellation law, I get 1 congruent to a to the power j minus I mod m, and the same is equivalent to a to the power j minus I congruent to 1 mod m. And here j is strictly greater than I, meaning is that this j minus I is positive at less than r. So we have by our assumption that r is the least positive integer for which a to the power r is congruent to 1 mod m. But here we have got an integer which is less than r, it is j minus r, such that a to the power j minus r is congruent to 1 mod m. So this actually gives a contradiction. Why it is so? Because r is the least positive integer for which this congruence holds, a to the power r congruent to 1 mod m, and here j minus I is less than r, so we have a contradiction. Okay, as we have 0 less than j minus I less than r. Therefore, we must have a to the power I incongruent to a to the power j mod m for all I and j are distinct, and I and j lie in the range 0 r minus 1. Okay. Then the second one, suppose n is a positive integer, then as n is a positive integer, r is also least positive integer, satisfying that congruence, r is positive. So by division algorithm, positive integer, then by division algorithm, there exist unique integers, q and r such that n is equal to qr plus s, where this, and therefore a to the power n is equal to a to the power qr plus s equal to a to the power r whole to the power q into a power s. Okay, a power s. And so what I could write, this will give that a to the power n congruent to a to the power s mod m. Why it is so? Because if I divide both sides by m, then I will get this a to the power r congruent to 1 mod m. That will give a to the power r whole to the power q congruent to 1 to the power q, means 1 itself, 1 mod m. So this will give that it is congruent to a to the power s mod m. So we have the second result. Now for the third one, number 3, a to the power n congruent to 1 mod m. Let us consider a to the power n congruent to 1 mod m. Now we already have by division algorithm n equal to say qr plus s, where s is lying in this range, and so a to the power n is congruent to a to the power s. Actually it will come out to be a to the power s. Okay, let me show it once. A to the power qr into a to the power s. So that will give that if I divide both sides by m, then a to the power qr will congruent to 1. As a result, what will be left? A to the power s mod m. Why it is so? As a to the power qr congruent to 1 mod m. So as by our assumption, a to the power n is congruent to 1 mod m, so left hand side is now 1 congruent to a to the power s mod m. But we have a to the power r congruent to 1 mod m, and r is the least positive integer for which this congruence is satisfied. But here s is a number which is less than r. S is an integer which is less than r, and here we have a to the power s congruent to 1 mod m. And this is possible only when s is equal to 0, because if I put s equal to 0, then the left hand side will take the form 1, and definitely 1 minus 1 is 0, is divisible by m. So S is equal to 0. This gives that n equal to QR. This gives that R divides n. So if I assume that a to the power n congruent to 1 mod m, that implies that R divides n. Conversely, suppose R divides n. Conversely, let R divides n. This will mean that for some k, we have n equal to Rk. For some integer k. For some integer k. Now, as R is the order of A, so a to the power R congruent to 1 mod m, and that will give that a to the power R whole to the power k is also congruent to 1 to the power k mod m, a property of congruence, and that will give that a to the power Rk is congruent to 1 mod m, and that will give that a to the power n congruent to 1 mod m, because we have n equal to Rk. So here is Rk, in place of Rk we have put n. So it is an if and only if statement which is proved. Now for the last one, number 4, let us take B congruent to A mod m, and this will give that B to the power n congruent to A to the power n mod m. It is also a property of congruence, and this is true for all positive integer n. Then B to the power n congruent to 1 mod m if and only if a to the power n congruent to 1 mod m. And from this result we shall get that order of B mod m is equal to order of A mod m. Why it is so? Because if in particular I take R to be the order of A, then I will get a to the power R congruent to 1 mod m, and this will imply that B to the power R congruent to 1 mod m. Conversely, if B to the power R congruent to 1 mod m, that will imply that A to the power R congruent to 1 mod m. So whatever is the order of B, that will also be the order of A. So these are actually simple results which we have proved on order. Now we come to the topic primitive roots. We already have learned about order of an integer. Now if it happens that m is a positive integer and order of an integer is equal to phi m, where phi is the Euler's phi function, then we say that that integer is a primitive root mod m. So let us define, let m be a positive integer and let a and m are relatively prime. So it is the primary requirement, they must be relatively prime. Now if order of A mod m is phi m, then A is called a primitive root of m, called a primitive root of m, or m has primitive roots, PRI. So in the earlier example we have seen, let me show the example once again. What is phi 7? We know it is 6, because for a prime p, phi of p is equal to p minus 1. So for the prime 7, phi of 7 is equal to 7 minus 1 means 6. Okay. So let us find out the integers whose order is 6. So in this list we have seen order of 3 is 6, 6 is phi 7, okay, equal to phi 7, and order of 5 is 6, phi 7. So order of two integers, order of the integers 3 and 5 are 6, equal to phi 7. So order of each of the integers 3 and 5 is 6, which is equal to phi 7. Therefore we can say that 3 and 5 are primitive roots of 7. Here, so we have got one example of primitive roots. 3 and 5 are primitive roots of 7. Clear? Three and 5 have order 6, which is equal to phi 7, This implies 3 and 5 are primitive roots of 7 or primitive roots mod 7, or we can say primitive roots mod 7. Now we discuss one result. This is theorem. A is a primitive root of M if and only if the set A square A cube up to A to the power phi M is a reduced residue system mod M. So first we consider that A be a primitive root of M. Then we are to show that this set is a reduced residue system mod M. Okay, so we have seen that A and M are relatively prime. Why it is so? As A is a primitive root. A is a primitive root. This is the first requirement, to have order of A for primitive root also, and that will give that A power I M are also relatively prime, and it is true for all I goes from 1 2 3 up to 5. Next, if A power I congruent to A power j mod M, means we have seen that every integer in that set is relatively prime to M. The first requirement for a set to be reduced residue system is that every integer in the set must be relatively prime to M. So that is satisfied here. So first condition is satisfied. Then second condition was that any two of them must be incongruent mod M. So let us consider it possible that two integers ai and aj, a to the power j, are congruent, where I and j are distinct, and I and j are, say, integers lying in this range. So let us take, for our convenience, say I is less than j, strictly less than j, so that j minus I is positive. Okay, then this can be written as A power I congruent to A power I multiplied by A power j minus I mod M, and here I have A power I is also relatively prime to M. Why it is so? Since A and M are relatively prime, that will immediately imply A power I is relatively prime to M. And so by restricted cancellation law, we get 1 congruent to A power j minus I mod M, and that actually gives A power j minus I congruent to 1 mod M, and here I have j minus I is less than 5. Okay, j minus I is less than 5. So as we had that A is a primitive root mod M, so the order of A is exactly phi m, but j minus I is an integer which is strictly less than phi m. So we have a contradiction, because for no positive integer less than phi m we can have the congruence this. So we have a contradiction, and this contradiction leads us to say that any two of those integers in the set must be incongruent for distinct I and j. Also, how many integers are there in that set? Also, there are how many integers? There are phi m number of integers in the set a square up to a to the power 5, because here the lowest power on a is 1 and the highest power is 5. So all total there are 5 number of integers. So the set a square up to a to the power 5m is a reduced residue system mod m, because we know that in a reduced residue system mod m there are exactly phi m integers. Now for the converse part, let us take that this set is a reduced residue system mod m and we have to show that A is the primitive root mod m. So converse part, A square up to A power phi m is a reduced residue system mod m to show that A is a primitive root mod m. A is a primitive root mod m. Now as A and m are relatively prime, why it is so? Because this is a reduced residue system mod m, so every integer in this set is relatively prime to m. A is an integer in this list or in this set, so A must be relatively prime to m. And as A is relatively prime to m, so by Euler's theorem, A to the power phi m congruent to 1 mod m, and here A and m are relatively prime. Now we want to show that there exists no integer, positive integer less than phi m, for which A to the power that integer is congruent to 1 mod m. So it is enough to show that A power I incongruent to 1 mod m, where r is positive integer but less than phi m. Now if possible, let A power I congruent to 1 mod m for some r which lies in this interval, in this range. I cannot say interval because r is not a real number, r is an integer. So in this range, then A power r congruent to A power phi m mod m. Why it is so? Because we have A power r congruent to 1, also A to the power phi m congruent to 1 by Euler's theorem, this one, okay. So both must be congruent, mod m. This gives a contradiction. Why it is so? Why? Because I have r is less than phi m but positive, so r is a power, or means A to the power r is a member of the set which is a reduced residue system, okay. So we have A to the power A to the power r, a member of the reduced residue system. A to the power phi m is definitely a member of the reduced residue system, and A to the power r is different from A to the power phi m. Why? Because r is strictly less than phi m. So what we have seen, it is a contradiction. Why? As this set A to the power phi m is a reduced residue system mod m. So r may be any positive integer starting from 1 up to phi m minus 1, which is different from phi m. So we have seen that two integers in this set are congruent, which is a contradiction, as it is a reduced residue system mod m. So we have seen that A to the power r incongruent to 1 mod m, where r is less than phi m but positive. So phi m is the least positive integer for which we have A to the power phi m is congruent to 1 mod m, or I can say that hence order of A mod m is phi m, which gives that A is a primitive root of so thank you everyone. Let us stop here.